talk. So now it's time for the next speaker, Professor Carolyn Beck from the University of Illinois at Urbana-Champaign. She will talk about modeling, analysis, and control of epidemic process dynamics.
Okay, so first, thanks to the organizers for inviting me to speak at the symposium. So as Zoe said, today I'm going to be talking about data-informed modeling and analysis, mostly analysis of epidemic dynamics. And this is work that was done as part of a C3.AA DTI funding grant from the first round of funding. And this is work, and this is completed with my collaborators and colleagues from that grant. Okay, so this is the title of the project. I'm not going to say much about this, and pretty much the main goal of the project is shown in the sentence here, and here's just a few of the publications that have resulted. And I think Prashant is going to be talking later today, and we'll probably have a whole different set of publications you can point to from some of the work he's focused on. So what we've been focused on is really trying to understand the dynamic evolution of disease processes. And we want to do this so that we can better predict and then better control the outcomes. And so we're looking at these from a dynamical systems analysis perspective. So we're looking at what are the equilibria for the model, what conditions do we need for convergence to these equilibria. We've looked specifically at what role the underlying human contact network plays in these dynamic processes and the spread of the disease. So we'll see a little bit of that. And then we've also looked at what if there are multiple viruses or mutating strains of the virus existing in the population. And I won't have time to talk about that, but I can talk about it afterward if people are interested. So everyone's probably pretty familiar with this picture. So this shows the progression of a disease modeled as an SIR process, so susceptible, infected, recovered process. And it basically shows the proportions of the population over time that are susceptible, so healthy, but possible to become infected, infectious, and recovered. So pretty much for the last 2 years, we've all been focused on this bottom purple line that shows like the proportion of the population that's infected. But of course, we know this isn't what it's looked like. This is more what we've seen, right? So these are the numbers of the infected over the last 2 years as they've trended in the United States and Germany. I just picked a couple of models. I don't know how well you can see this, but I think this is from about 4 or 5 days ago. Obviously, Germany was trending up quite a bit again. So clearly, the classic epidemiological model for viruses, that of the SIR model, is not capturing these trends. And so that's what we're trying to do is maybe develop better models or understand like what we need to know to predict these outcomes better, or at least to look at control policies for various scenarios, given that we know we need different models. So one of the things we looked at, as I said, is what role network structure plays. So specifically, we've been looking at trying to quantify this in terms of, say, is there some function of the underlying adjacency matrix, say W, that describes the interconnection between subgroups of the population or individuals in the population? So is there some underlying function that we can compare to some function of the disease model parameters that will tell us something about what we expect to see in terms of, say, convergence to some of the equilibria. So I'm going to start by just reviewing the SIR model. As I said, that's the classic virus model that epidemiologists have used for over 100 years, probably. And then we'll look at one modification to that, specifically for COVID. And then we'll look at using some dynamical systems approaches to computing the equilibria and looking at what conditions we need for convergence to those equilibria. And then we'll talk a little bit about some networked versions of these models. And as I said, I won't have time to talk about the multi-virus or multi-strain models. Okay, so in the SIR model, we assume everyone in the population is either in the susceptible compartment, the infected compartment, or the recovered compartment. And the susceptible these didn't quite render right. The susceptible become infected at a rate beta when they come into contact with the infected population. The infected transition to the recovered compartment, so they recover at a rate gamma. And then if immunity isn't permanent, then the immunity will dissipate at some rate delta, and people become susceptible to the population again. And so the classic model for the SIR, the classic mathematical model shown then in this box, we have 3 compartments, we have 3 differential equations. They're mildly nonlinear, and so these describe the dynamics. And I should point out that we assume throughout that these variables, S, I, and R, are representing proportions of the population. So there's an additional constraint in this model that at any given time t, the sum of S, I, and R will be equal to 1. Okay, and so because it became pretty apparent early on with COVID that there was some big portion of the population that was asymptomatic but infectious, and that this was contributing to spread of the disease in ways that weren't quite understood as well as the usual SIR model, we, along with many others, said, okay, let's look at a model that incorporates this asymptomatic proportion of the population. So again, we have a susceptible proportion of the population. We assume it transitions to either an asymptomatic infected compartment or a symptomatic infected compartment at some rate beta, but now we're assuming there's some proportion Q that becomes asymptomatic and the rest become symptomatic. And then the asymptomatic may transition directly to the recovered phase. So there are people that never really presented symptoms, and so we're assuming that they're transitioning or healing at a rate kappa. Again, the symptomatic infected, they're healing at a rate gamma, and then we have the rate of essentially loss of immunity. And so now we have 4 compartments, and we have 4 differential equations describing the model. They're similar structure. These are proportions again, so at any time t, S plus A plus I plus R is going to be equal to 1. And so we've gone from a 3-compartment model with 3 parameters that if we're going to try to estimate models for, say, COVID from data, we're going to try to estimate for the SIR 3 parameters from the data. Now we have 6 parameters. We've just introduced 1 more compartment. We have double the number of parameters we're going to try to estimate from the data. Okay, so as we're probably all aware as well, trying to estimate these parameters from the data, especially early on with COVID, was a bit problematic. There are a number of issues with the data. We don't have a random sample from the population, right? We mostly were just testing people with symptoms. There's missing data in particular for us. There's no asymptomatic data in that case. These are dynamic processes, so there's sample-to-sample temporal interdependence, et cetera. And even if we didn't have these issues under ideal conditions, there are identifiability issues, in particular early on in an epidemic, with trying to estimate the disease parameters from the data. So we've tried to use both estimation processes and refer to virologist advice or virologist literature and try to combine the information to come up with parameters for our models as we've gone through this process. So assuming that we have a somewhat random sample, but we don't actually really have direct asymptomatic data, we can estimate the proportion of the asymptomatic. And Nesterov proposed a pretty straightforward method early on in the pandemic, and we've used that to estimate the proportion of asymptomatic. It's really pre-symptomatic. But once we know that proportion, Q, we can actually estimate some subset of the rest of our model parameters just using ordinary regression or system identification approaches. We still really can't estimate delta at this point. That is the rate at which we lose immunity. And in particular, we all know we've had mutating strains. So we've been looking also, some of our ongoing work at trying to quantify the effects of using non-random sample data. And then we've also been looking at maybe trying to design active or optimal testing policies so that we can improve the information that we get from the data. And Eric has a poster on this. I don't know if Eric's here right now, but he has a poster on this in the poster session. Okay, for going back to the classic SIR model, we probably are all familiar with this as well. I mean, this is, as I said, this analysis has been around 100 years. We can apply basic high school calculus and come up with a sufficient condition under which we can show that this SIR model will converge to the disease-free equilibrium point. So we want the proportion of infected to go to 0. So we can come up with, as I said, just using basic high school calculus, come up with a sufficiency condition. Everyone knows this is the basic reproduction number. And basically it says if the ratio of the infectivity rate to the healing rate is less than 1, then we will converge to the disease-free equilibrium. And so this analysis guarantees us asymptotic stability. And as I said, this was completed about 100 years ago. If we use Lyapunov methods, we can actually show the same condition guarantees exponential stability, which means we converge a lot faster to that equilibrium point, which we care about, right? We really don't want to wait till infinity to converge to the disease-free state. If we don't satisfy this condition, then we need to talk about the endemic equilibrium and what are the conditions to converge to the endemic equilibrium. So we may have endemicity in that case. Okay, but rather than analyzing that for the SIR case, let's consider again, the SAIR and look at how just adding this one additional compartment complicates these analyses. So again, with the SAIR model, we have 2 equilibria. We can show we have 2 equilibria, the disease-free equilibrium and an endemic equilibrium. And so the disease-free equilibrium, of course, the asymptomatic and symptomatic infected compartments at this equilibrium point should be 0. And so if we want to analyze what conditions do we need to converge to the disease-free equilibrium, now the equations are a little more complicated, so we use nonlinear systems analysis. We look at the Jacobian for the system dynamics and evaluate that Jacobian at the equilibrium point. And so taking into account the fact that we know there's this constraint between the proportions or the variables in our dynamical system, we only really need to evaluate a 3-dimension model. And so evaluating our Jacobian at our disease-free equilibrium gives us this constant valued matrix. We just have to look at the eigenvalues. Doing that tells us if we want to guarantee asymptotic stability to the disease-free equilibrium, then we need to have this condition met in terms of the disease parameters for the SAIR model. And so notice that, again, we have essentially a sort of a beta over gamma sort of conditions. So that is the rate of infection over the rate of healing should be less than 1 for convergence to the disease-free state. And again, we can use Lyapunov analysis and get exponential stability conditions. And so here's just some quick simulations that show that when we don't have convergence to when we don't meet the criteria for convergence to the disease-free equilibrium, and when we do, and notice that the axes are quite different. So in the top, at the end, we're at some point after 3 months. In fact, we have 90% of the total of the population is infected. And in the case where we do have, we meet the condition, after, say, 200 days, we only have 5.5% of the total population that's been infected. So that's the difference that it makes if we meet the conditions for convergence to the disease-free state. Okay, so the endemic equilibrium for this model. So this is pretty ugly. This is what the equilibrium point looks like. That's the endemic equilibrium point. I guess a couple things to point out is that both the asymptomatic and symptomatic infected compartments are proportional to delta. So if our immunity is permanent or near permanent, these values will again be essentially 0. So it essentially becomes a disease-free equilibrium again. And so that's true. When you have permanent immunity to diseases, typically, then the disease-free equilibrium is always the point to which the disease converges. And again, note in this case, because it's endemic, we have sort of the inverse. Beta's in the numerator, the healing rates are in the, beta's in the denominator, the healing rates are in the numerator. Okay, and so doing some simulations with respect to endemic equilibria, and we have also computed the conditions that we need to meet in order to converge to the endemic equilibrium, but they look even worse than the actual equilibrium point. So, so just looking at some simulations, if we assume that we have immunity of, say, 10 days, this looks pretty bad after, a year and a half. We've settled at the equilibrium, the endemic equilibrium, with about 30% of the population being infected in steady state. If we assume immunity lasting about 3 months, it's better. After about a year and a half, we see that about 7% of the population remains infected in steady state. Okay. If we assume that immunity lasts about 6 months, okay, and so this is, I think, what people are starting to think about the COVID strain so far. And we recomputed some of our parameter estimates and used some literature to use parameters that from more recent data, so probably Omicron. Then what we see is that it takes a long time to settle to the equilibrium. We're looking at like 2 years here. And we see some, peaks in infection that occur multiple times. But in the end, it looks like we settle to a steady state equilibrium with maybe just 2 or 3% of the population that's infected. Okay, so how do we incorporate networks? All I've talked about so far are the single group compartment models, okay? And so in the single group compartment models, what we're assuming is that all individuals in a population interact with all other individuals equally, okay? So we're completely well mixed, which we know isn't true. And so that basically assumes that the underlying contact network that we're living in is a complete graph, okay? So alternatively, we look at what if we assume that the underlying topology of the human contact network is arbitrary, and what I mean by arbitrary is there's no pre-assumed structure. It's not a line, it's not a circle, it's not even a small world graph. We're just saying it's arbitrary, right? And there are many levels at which we can model these contact networks, from the human contact between individuals to, say, aggregated population centers. And there's infrastructure as well that can contribute to this, this contact network that we consider. And so in most of our work, we assume that we're dealing with aggregated population centers, so not human individuals. So just some notation. We assume then that we have an interconnection of subgroups or possibly individuals that's given by some weighted graph structure with adjacency matrix W. So what that means is that the elements of this matrix W, the Wij, they indicate the strength of interaction between the two respective nodes or subgroups in the population. Okay, so we want to look at how to bring that network structure together with this SAIR model. And so what we have done is we've used what's called a mean field approximation model. Okay, and so there's been a lot of work over the last 20 years in bringing together underlying interconnection networks and the classic compartment epidemiological models. And so, there's a probabilistic analysis that shows how we converge to the mean field approximation models, which I'm obviously not going to get into. So again, here we're going to assume any given node I in the network has proportion asymptomatic, symptomatic, we call that P now, so it represents proportion of symptomatic infected or probability of symptomatic infected, and recovered, and we have this constraint again at each given node with respect to the proportions of the populations. And there's some details here we're glossing over in terms of how to account for different sizes of populations at each node, but we won't get into that. So for each node in the system, we assume there's an SAIR dynamic. And so these are the differential equations that govern those dynamics. And the interconnection structure then is explicitly affecting sort of the rate of infectivity amongst the susceptible and infected proportions of the population, right? It directly enters into the dynamic equations now. Okay, so if we have n nodes, we're going to have a set of n of these three equations, so a 3n dimension dynamical system model. It gets pretty hard to write, so just again some notation. We put it into matrix form. So basically, we're just stacking all these equations up together, and you know, all our parameters are now in diagonal vectors. I should say we also allow for heterogeneous rates, so the nodes can have possibly differing parameter values. Can I go back? And then we stack up the variables, the asymptomatic, symptomatic, and recovered dynamic variables of the system also in matrix and vector notation. So that gives us a set of 3 vector differential equations describing the dynamic process over sort of a larger networked population. And then going forward with stability analysis in order to understand now, let's just say convergence to the disease-free equilibrium. We considered a Lyapunov approach, so he's fairly standard quadratic Lyapunov function, and we can show that, that this condition is sufficient for convergence to the disease-free equilibrium. So basically we have a condition that's in terms of the interconnection structure and the parameters of the disease dynamics, okay? And so these are basically block diagonal matrices of weighted basic reproduction type number values. And so again, we have a spectral condition on our adjacency matrix that we need to meet that's based on values of the disease parameters if we want to guarantee convergence to the disease-free equilibrium. So it's, as we said in the beginning, we're looking for some function of the adjacency matrix in terms of the disease parameters. Uh-huh. Oh, sorry. Okay, I'm pretty much done. Yeah, I know there's usually have a clock on your, oh, I see it. Oh, I didn't know it was there, sorry. Okay, yeah, so as I said, yeah, we're not talking about the mutating strains and no discussion on controls. Actually, I had some conclusions, but we'll just finish there. So thank you.